Hello everybody! In this final video on the influence of Thomas' theory over the development of density functional, we will see which are the limits of the Thomas-Fermi approach and the paths, the ideas that were taken to try to counter these limitations, these drawbacks. To do this, the easiest way is to start from the exact density functional and compare with the Thomas-Fermi functional to see where the limits arise. Let's write the exact total energy as a functional of the density. We know from the Hohenberg and Kohn theorem that this is indeed exact. Let's then compare it with the Thomas-Fermi approximation. We easily recognize that the Hartree term and the external potential term are the same in the two approaches. But, most importantly, we immediately see where the limits of the Thomas-Fermi approach lie. First of all, in the Thomas-Fermi formula, there is no exchange and correlation contribution. Already for total energies of simple atoms, this is quite an important term. In particular, the exchange contribution cannot be neglected. This missing term was of course completely acknowledged immediately after the publications of Thomas and Fermi. Already in 1929, Felix Bloch, yes, the guy of the Bloch theorem, proposed the functional of the density to take care of the Pauli repulsion among electrons. Actually, at the same time, and independently, also Paul Dirac proposed an extra contribution to the Thomas-Fermi energy functional to include exchange. Strangely enough, today, only Dirac's contribution is acknowledged, in spite of the fact that in Bloch's article, everything was already there. The functional of the density has a power of 4/3, as well as the prefactor. Both original articles from Bloch and Dirac are quite difficult to follow in their justification for the extra exchange term. In the lecture notes, however, and in the exercises, you will see that already with dimension analysis, it is possible to justify the power of 4/3 in the density. Be as it may, from 1930 on, this was known as the Thomas-Fermi-Dirac approach. We have then a new energy functional of the density that contains an approximation for the exchange and correlation part. We can now address the second source of approximation, which is the kinetic energy. We have seen that the Thomas-Fermi or Thomas-Fermi-Dirac approach assumes a very simple functional for the kinetic energy, which turns out to be a very rough approximation. Among the most spectacular failure is, for instance, the fact that no bonds among atoms can be predicted by the Thomas-Fermi theory. So no molecules or solids, which is clearly wrong. And in fact, not long after realizing this, Carl von Weizsäcker proposed in 1935 a correction to the kinetic energy that depends on the gradient of the density, and that permits to obtain quantitative improvements. For example, bound molecules are now possible. It is very interesting to notice that this was not only the first example of density gradient expansions, which will be later extremely successful in DFT, but also the first example of the application of the Thomas-Fermi approach in a completely different field. Von Weizsäcker, in fact, proposed to use the Thomas-Fermi formula to calculate the mass of nuclei in the liquid drop model. But he had to correct the much too rough description of the kinetic energy with a gradient correction. The Thomas-Fermi-Dirac-Weizsäcker theory was born. That here we see again in the density functional formalism. To be fair, the systematic correction of Thomas-Fermi via a gradient expansion is not viable at all, for this series diverge. But this didn't stop the developments for correcting the kinetic energy. One of those, for example, is quite recent and concerns indeed the correction of the kinetic term as proposed by Julian Schwinger in the early 80s, via a couple of articles. I like to cite those two articles, which are very interesting to read, and also because Julian Schwinger was, among many things, also Walter Kohn, PhD advisor. Let's then conclude this historical excursus on Hoevellin-Thomas and his density functional. We have seen that Thomas' approach, his statistical approach for the electronic structure, pioneered and influenced the later development of density functional theory. Even if the theory was based on a semi-classical approach, its deep physical content and promising results deserved further improvements and corrections. Today, DFT has largely outperformed the Thomas Fermi approach, in particular for the electronic structure problem. It is, however, interesting to notice, in this historical reminder, that here and there new developments in the Thomas Fermi are emerging, like in superfluidity, or even the more exotic supernova matter. So, we close for the moment this historical overview. Have a look at the lecture notes and don't miss the exercises. Goodbye.